of science. Today, I will give a very brief introduction to my work recently. The name is the Development of Application of the Molten Tense Machine Learning Tensors. Actually, this work was done during my group, with led by Professor Peitao Liu, also with 3 PhD students. I will introduce from these 5 aspects. Well, it's well known, actually, as a starting point, this DFT calculation is showing many advantages, such as it can obtain reasonably equivalent energy, forces, stress tensors. Up to now, let's say most of application, DFT still remains the method of choice, but the DFT also have some kind of shortcoming. Up to the day, it is still slow. Also, it's challenging for calculation finite temperature properties. It can be obtained in this chemical accuracy is about 1 kcal or per mole. Due to this limitation, so in our field, this challenging is still existence, especially for multi-scale computing. If we take silver alloy, for example, we know this kind of alloy is multi-component alloy, typically include over 10 transition elements, and also with very large spatial or temperature scale. Typically, for example, you need to describe these systems at least larger than 10,000 atoms. The time scale is about 1 nanosecond. But this DFT calculation is only can limit, treat atoms is about 1,000, and the time less than 100 picosecond. And so during the past 40 years, people try to use molecular dynamics, and these kind of things, the rate of in the atomic potentials. But it's very tough to develop the efficient and equivalent in the atomic potentials. That's the reason during the past 30 years, people do developed this empirical force field. And this kind of potential is high efficiency, but is low accuracy. And this potential normally is simple, but inflexible. And during the past 10 years, also people try to combine this ab initio calculation with the machine learning together. We call machine learning force field. And this they can achieve very nearly scaling for high efficiency and high accuracy. And also this kind of potential, which can be descriptive and flexible data physics-driven models. Then I would like to turn back the history about the first work, which most focus on machine learning force field with the high dimension neutral network potential developed by Professor Michel Parinello. Professor Parinello, which is they made a great contribution to our DFT calculation because he developed the guy's AIMD simulation. During this kind of machine learning force field, he proposed the total energy of the system is the sum of the local atomic energy, and then introduce the translation, rotation, or permutation environment atomic local structure descriptors, which is include is all kind of atomic center symmetry functions. This kind of framework is solving the long-standing dimension and the transferability problems. As in our field, for this machine learning force field, actually, we have the very general development process. We call 3 steps. The first one, you need the construction of the reference database. And the second one, you need to try to find representation of the atomic environment. Finally, you need a regression, which is a model learning of the potential energy surface. Normally we call PS. But we obtained a current machine learning force field. All these 3 steps are equally important, especially for first step, which is the most demanding one, usually a time-consuming try and error process based on the initial for standard pathway learning method. Here, I want to mention one thing is we call on-the-fly active learning within the WASP code. And the WASP code, during the past few years, we try to develop this kind of on-the-fly machine learning framework with actually combine this AIMD simulation. And for the kind of training structure, which is automatically selected on the file from the ab initio simulation. The purpose actually is try to cost little human intervention based on the very nice query strategy. And this method actually is very effective, almost during ab initio molecular dynamic simulation. These steps over 98% are passed by during the training. They only try to fit this training structure is 2%. And also in his method, we try to use Bayesian linear regressions. What is described in the WASP code is try to use separable descriptor, which is describe the local environment around each atom, can be mapped use 2 or 3 body distribution function. This is very successful normally, but in these systems, it's 2 body atomic distribution function or 3 body atomic distribution function. They are really enough to describe the whole structure. For the third, when you have described and you try to use regressions, and this method try to use the kernel-based method. This in the WASP code when he tried to training structure and directly compare to the local structure in the darkened materials and compare how the similarity use this weight factor W1 and W2 and Wn. Normally, for any kind of structure, if you have a very nice training structure spectrum, and then you can finally to construct this kind of formula according to this weight number. So this method is lies on the kernel function, which describes similarity, as I mentioned before, but they can really yield the high accuracy, but the efficiency is very low when the number of the kernel-based function is large. And then let's say this kernel-based method, which they use a lot of training structure, which is storage in this computer. And when you try to fit this formula, as the base set increase, for example, if you go to the multi-component alloy, such like a ternary compound and the 4-compound, even the silver alloy, then you become, the training becomes very costly. Then this system is very slow. And this result is less efficient, okay? This is the WASP problem. But if you do this system such as binary, okay, it's like periodical lattice structure, and then WASP is such as very effective. And so how to solve this problem? And then we try to use the momentum tensor potential. This kind of potential, they have the unparalleled advantage of the high efficiency. If we compare to different methods like GAP and the NMP, SNARP, if we go to here, this means the time is much less the cost, and the test error is here is low. This much high dedication, and compared to the oral kind of method is MTP, we show really a very good this kind of advantage compared to this kind different this machine learning method. So here I want to mention simply what is momentum tensor described. So this descriptor we just use as the sum of the mu order momentum tensor of the neighboring atom relative to the center atom. As shown in this picture, when this kind of structure, you have the center atom, they have different neighbor, okay? But though this neighbor distribution is not, of course, not only around in this plane, and also they have around this axis depend on this page, right? So they have two things: is threshold function, and also this latent mu times this factor. This mathematical description, if we compare to the physics concept, we say when this mu equals to 0, this actually corresponds like the total mass of the system. Okay, it's a static moment. If the mu equals to the first momentum, okay, then they describe the rotating part, which is the center of the mass. If the mu equal to second, the 2 is second momentum, which can be described the moment inertia, this case. And finally, you could build this matrix like this way. So, for example, in this case, we chose 3 by 3. But the difference means you try to use momentum tensor potential in the machine learning framework. This MTP still need performing contraction between different moment tensor. Okay, they coordinate independent basis function. For example, in the systems, whatever you use different the reference systems, finally the energy should be the same. Okay, and another thing is because you try to use the performing this contraction, then they give you the chance to fit this structure and energy, use a linearly regression model. This reason because this momentum tensor descriptor, they have showing very highly descriptive nature. Also, then these kind of things with accelerating your simulation, which is high efficient. Okay. Of course, during our work, actually, we found this kind of method that still have some kind of problem. That especially for generation or scalar base, is not systematically optimized. And during our work, so we also try to use genetic algorithm and simulation and nearing method. For this optimal calculation path is obtained such as the number of the equivalent component of the all tensor is minimized as shown in this tree structure. Yes. First, you have a lot of tensor momentum. Okay, then you make a construction. Finally, you get the scaling based unit station. For example, in our case, if we compare the first things, we try to the same computer at the same systems. If we compare to our improved MT model compared to original one, the showing is enhanced nearly by a factor of the 2. Okay, and then if we compare to the kernel-based method, which is used in the WASP code, we improved that MTP is about nearly 20 to 100 times fast, at least compared to our test case. And then we write the code we call MTP code, which is based on the Institute of Metal Research, Chinese Academy of Science. And we use the C++ and the Python code. And our code, which is about 65,000 line, this code number. So in our code, we conclude this about 5 function. The first thing is training structure generation. And then the active learning, which is we use on-the-fly learning technology, combined AI-MD, find the training sample. And then we try to use MTP code optimization technology, which is the fit potential. And we also include validation of predictions. And then we try to use the first case of zirconium. For example, as he showed at 0 pressure, and this pure metal at a phase transition from HCP to the BCC is about 1,136 Kelvin. And then we use our potential simulated only need of 935 training structure, which is much less than normal way. And we get a very efficiency if we compare to the energy force and the stress, which nicely fit to the DFT result. And then we also calculate lattice constant is energy with its value and the phonon dispersion, and finally fit variable. Okay, according to this, and then we try to simulate the phase transition with temperature increase for the heating this process. We get the phase transition temperature is about 1,100 Kelvin. And then we can go to cooling down. And from the high temperature to the low, the phase transition is about 982 Kelvin. Average is 1,045 Kelvin compared to experiment. Let's say it's very nice. We never say V calculation is really exactly the same to experiment data. I don't think that is correct. If you really get this very the same structures, the data, because the calculation, they also have some kind of shortcomings compared to experiments. And the second thing I want to show the case is CO, this gas absorption of the RH metal. This is a very long-standing CO puzzle problem in our field. In this CO, because absorption, experiment always, this CO position is not always in the top position. but we used all kinds of different calculation. They all get the whole positions. So these questions exist in our field is about 30 years away. Such quite long as no one really resolved this problem. According to our method, and the first things we try to fit this kind of machine learning method. First things we use on-the-flying active learning and use normal low-cost method such as standard GJ and RDA method question. And for this one, finally, we get this random phase approximation, and this we call the high equivalent method. You compare this difference, you see, we just learning this difference, okay, from the select a few point, learning this difference. So we call delta learning method. And according to this, we try to solve this problem. For example, we not only get the right this absorption energy compared to experimentally, as also we get the right position. Okay, we don't know the underlying the physics in this kind of problem during the traditional DFT calculation. But the machine learning method, it only gave you a chance to fix these long-standing questions. And also, not only for this kind of position, we can get the right top position absorb the CO gas. And if you increase the concentration on the surface, which is compared how to the change system, we also get a right structure compared to experiment data. This is the classification. The third case I will show recently, we collaborated with Professor Zhou Liang in the Northeast University. They try to experiment, investigate this lanthanum titanium oxide for very good phantom thermal conversation materials. They create a record water evaporation rate with this kind of evaporation. But these materials really attracted our attention because when you increase temperature and pressure, this induces reversible phase transition. For example, you increase temperature, from the beta to the lambda phase transition. And you increase the pressure, they also show you phase transition. Not only for this, when you use the laser light, you get very ultra fast structure change from the beta to the lambda. The time scale only 0.5 picosecond. It's very fast. So this material, they're showing very interesting ultra fast and reversible solid phase transition. That's our want to know what kind of structure phase transition path and the microscopic mechanical mechanism still is unclear. And then why this can be appeared in this reconstructive the solid phase transition. Normally, solid phase transition actually is very difficult because they need a mechanical energy barriers. And so we use our this MTP modeling and try to use on-the-flying machine learning together and try to simulate this solid to solid phase transition. We also use the metadynamic sampling technology and include the momentum tensor potential. We try to fit this problem, only need 3,775 excitation. Okay, and then you will precisely to compare to experimental. And this, we get experimental phase transition at the temperature And also we found these titanium 3 dimer rotation actually in the plane, very important to induce the phase transition at just very low this temperature areas. And also use this large dynamic simulation, use MTP potential. We found this kind of transition is easy, this really special. They just layer by layer education. It's very, it's new kind of things. Finally, and also we compare this kind of method to the topological phonon materials during the time limitation. So I just go fast. We predict the new topological phonon materials, and we build the phonon database. In the case, if you are interested, and you can go to this website to look this database and the code showing the structure, all kind of details, how to calculate, how to analyze this. We also use the AI-aid analysis for topological phonon. Then I would to mention the final result. According to this, is 3 years ago, we theoretical predicted phonon, topological phonon, and in this graphene. It's only theoretical work. And recently, we compare to experimental use 40 years. We've really confirmed our predictions. Okay, fine. I will conclude our presentation. Thank you.
Thank you very much. So about your zirconium, the MD simulation result. So the cooling and heating, the transient temperature was debated. So is the physical meaning or is it just artificial?
Well, this depends on how far the increased temperature, because it's some dynamics canonical processes. Yes.
Okay, another short question. Thank you very much for Professor Chen's impressive talk regarding this development and the application of momentum tensor machine learning potential. I have two simple questions. The first one is that have you ever compared the efficiency between your development method with the state-of-art DPMD, the efficiency difference?
Yes, we tried it, but not to make the systematically compare for this kind of method. At least now we get about 25 times.
Oh, 25.
Yes.
Oh, that's cool.
For our case, okay. But this was since we needed to do a lot of tests, okay, not only for one case.
All right. So the second question is that for your high order functional machine learning training, what the database, any difference between the regular functional GGA? I mean, the database set, the amount of the database set.
Yes, but for this kind of the machine learning from the low accuracy method, but much more efficiency. And during this part, we select a few very crucial structure and then use the RAP method, which is cost timely. I mean, consuming so large. And we selected a few, about 10 structures.
Okay.
Yeah.
Thank you.
Okay, you're welcome.